Hello, everybody, and welcome to our lesson today on solving systems of equations by graphing, which is part of our ongoing study in functions about modeling and predicting change. And so let's go ahead and begin with what we already know about linear functions and modeling and predicting change. If we see here in this particular problem, it says Nelson is standing at the 20-yard line and runs at a rate of 2 yards per second. How far will he run after 10 seconds? So we know if we were going to write this as a linear model, since it has a constant rate of change, which is the 2 yards per second, and Nelson is starting at the 20-yard line, we would simply model it with y equals 2x plus 20. And then since we are wondering how far he will run after 10 seconds, our prediction would be y equals 2 times 10 plus 20, because we're going to simply insert the 10 for where the x is. And then we come to the conclusion that after 10 seconds, Nelson will run 40 yards. So our model is y equals 2x plus 20. Our prediction is 40. Our conclusion is that after 10 seconds, he will run 40 yards. But here's what we want to consider today, is how can I model two or more events that share a common solution? And the way we're going to model two or more events that share a common solution is using what we call systems of equations. And what a system or systems of equations, you'll hear it referred to both ways, is that it occurs when two events are occurring simultaneously. And that word simultaneously is just a big word for together at one time. And it is the solution to a system of equations that's an ordered pair that makes both equations true. So what we're going to be doing for this week and next week, and then even a little bit into January, is finding the solutions to systems of equations, which means we're going to be finding an ordered pair, which is an x and a y value, that's going to make both equations true. All right, so let's look at our first example here. It says here, during the annual hot air balloon rodeo, numerous hot air balloons are in the air. One balloon is at an altitude of 20 feet and rising at a rate of 10 feet per second. Another hot air balloon is at an altitude of 100 feet and descending at a rate of 10 feet per second. The question is, after how many seconds will the two balloons be at the same altitude? And we want to solve this by graphing. So first thing we're going to do if we're going to solve this by graphing is we would need to write a linear model that represents each situation. Okay, so my first balloon there is going to be y equals 10x plus 20. All right, go ahead and do this on your slides at home as well. Okay, so y equals 10x plus 20. And that means that this first balloon is rising at a rate of 10 feet per second, and it is already 20 feet in the air. The second balloon is at 100 feet, and it is descending at a rate of 10 feet per second. So if it's descending, that means it has a negative rate of change. So we're going to have y equals 10x plus 100. Okay, so what we want to do now is take both of these linear models, open up Desmos, and we are going to graph both of these on Desmos and look for where they have a common point of intersection, and that's going to be our ordered pair solution to this linear model. All right, so let's go over to Desmos. And we're going to first type in our y equals 10x plus 20. And then y equals the negative 10x plus 100. All right, so there's our two linear models. And I'm going to zoom that out just a little bit and come right here. So if you look at these two lines, the first line, 10x plus 20, is represented by the green line, and the second line, negative 10x plus 100, is represented by the purple line. If you look right here at the point of intersection, And if you place your cursor on that point of intersection and click, it will make a gray dot, and it gives you the ordered pair for 60. Okay, so my x values are my seconds, and my y values are my altitude in feet. So what I can conclude there is that after 4 seconds, they will both be 60 feet in the air, and that is when they're going to meet. All right, so if I come over here, I can just put my prediction as the ordered pair for 60. And I will say the balloons will both be at 60 feet after 4 seconds. All right, so that's when the two balloons will meet at the same altitude, 60 feet after 4 seconds. And the type of solution here, this is going to be a one solution system of equations. Because if you look at your graph of the two lines, this is the only point they are going to intersect and meet, and they will never intersect again. Okay? So, as we look at this answer now, the ordered pair 460, let's apply a little bit more meaning to this. Because what we said here in our definition of a systems of equations, if you look here at the orange type, it says the solution to a systems is an ordered pair that makes both equations true. Okay, so here we had a true system, two things occurring simultaneously. One balloon is rising, one balloon is descending, and we have an ordered pair that's going to make both equations true. All right, so let's see how this works. Here's both of my equations. Y equals 10x plus 20, and I have y equals negative 10x plus 100. So my ordered pair here is 460. So 4 is my x value and 60 is my y value. So to show you how this ordered pair makes both equations true, I'm going to substitute 60 for x and 60 for y, and then 4 for x. And then I'm simply going to solve this equation. So I have 60 equals 10 times 4 is 40 plus 20. So 60 equals 60. My equation is balanced on both sides. If I come over to the other equation, the y equals negative 10x plus 100, and do the same substitution for my y and my x variable, all right, so what I see here with both equations is that this ordered pair of 460 satisfies or makes both equations true. Okay, so this is what we call a systems of equation, and the solution to the system of equations is that ordered pair that makes both equations true. All right, so that's our first one. All right, so let's go to our second one here. It says here, 2 fig trees are planted into the ground at the same time. One tree is 4 feet high at the time of planting, and the other tree is 1 foot high at the time of planting. Both trees grow at a rate of 2 feet per month. Will the two trees ever be the same height at the same time? Solved by graphing. All right, so my model for the first tree is going to be y equals, and it was 4 feet high at the time of planting, and it grows at a rate of 2 feet per month. So that's going to be y equals 2x plus 4. And then the other one is going to be y equals 1 foot at the time of planting and 2 feet per month. So 2x plus 1. All right. So these are going to be the two equations that I go over to Desmos and graph. So let's come over here to Desmos and reset to that. All right, so here's the line 2x plus 4. And then here's the other plant represented by 2x plus 1. All right, so notice what we see here. We see parallel lines. And we know that parallel lines never intersect. So, first of all, let's define this as the type of solution, which is no solution. All right, these two lines will never intersect. So what that means for my prediction is the two plants will never be the same height at the same time. Okay, actually that should be two trees. All right, the two trees will never be the same height at the same time. All right, if you also notice something here, both of these have the same slope or the same rate of change, which is 2x. So what we can also conclude here for type of solution where it is no solution is that whenever we have the same slope, we will have a no solution system of equations. And since it is no solution, it basically means that there is not an ordered pair that could be substituted into both of these equations that's going to make it a true statement. All right? So that one there is no solution. All right, so let's look at this one. This one says graph the following equations. Y equals 2x plus 6 and y equals 2 times x plus 1 plus 4. And the question is, do they have a solution? All right, so the first equation, y equals 2x plus 6, that is already in slope-intercept form and can be graphed. However, the other equation is not in slope-intercept form, and so it cannot be graphed as it is. So I need to change it into slope-intercept form. So what I'm going to do then is come over here and change it into slope-intercept form. So I'm going to write here the y equals 2 times x plus 1 plus 4. And I'm simply going to write this in the slope-intercept form by distributing the 2. So I have y equals 2x plus 2 plus 4. And by combining my like terms, I get y equals 2x plus 6. So that means I'm going to graph y equals 2x plus 6 on Desmos. And if I look here, the other equation was y equals 2x plus 6. So for something like this, y equals 2x plus 6, this is what we are going to call infinitely many solutions. So do they have a solution? The answer is going to be yes, they have infinitely many solutions. All right, and if you think about when we did multi-step equations, these are the same types of solutions that we had to multi-step equations. One solution, which made the equation true. No solution, which meant there was not any number that would make it a true statement. And then infinitely many, which meant many numbers can make it a true statement. So in a case such as this, if you look at your straight line, you could select any x or y value or any ordered pair along this line, and it is always going to produce a true statement. Okay? So that's what these mean when we have the infinitely many solutions. Okay? So what I want you to start with today, since this is day 1 about solving systems by graphing and systems of equations, is we're simply going to use the Desmos graphing tool, and we're going to find the ordered pair solution for the following systems of equations by graphing, and like you've been doing the past few days, inserting a screenshot of your graph. Now, don't turn the video off and think you know what you're going to do. Let me show you how I want this to look so you do it correctly. Okay, don't turn me off just yet. So what we're going to do here is you would come over here and graph y equals 1/4 x plus 2. And then you're going to graph the y equals the negative x minus 3. All right, then what I want you to do is come over here and make sure that the ordered pair solution is showing, like you see there, negative 4, 1. Screenshot. So when you screenshot your lines and the solution, just like this, so I can see that you did it. All right? Let me just do it this way. All right, so that's how I want you to put it in. Just like that. So I can see the equations, see them graphed, and see your ordered pair solution. Okay? If it does not look like this, you're not going to get a grade for this assignment. Okay? So make sure you follow the instructions and make sure all of your graphs look like this. All right? So I've put in here 8 of them for you to do. Again, this is just our first day of doing this. So it gives you some practice in, again, using Desmos and graphing lines, looking for that point of intersection, and identifying it using the Desmos tool. All right, so I will be on Google. No, I won't be on Google Meet today. But if you need anything, it is Wednesday. If you need anything, please email me and I will get back to you. I will be in some meetings today, but I will be monitoring email and I will get back to you as soon as I can. All right, have a great day, everybody. And I look forward to having something else for you tomorrow.